Okay, guys, good morning. So let's start our class. Let me share the screen. Okay. So if you can see, we have an announcement, and we will have our second quiz this coming Thursday, and it will be on lecture 5 to 8. Okay, and your assignment 1 is graded. It's available on the blackboard. Have a look at the assignment and also look at the assignment solution. Okay, look at the assignment solution. This is already posted. And please try to learn, where you did the mistakes. It's important. And remember, I am making the assignments and I'm giving the assignment problems which are quite similar to the type of problems that we ask in assessments, in the midterm exam or in the final exam. So, this is a good practice, and that's the reason I have included assignment as a component in our classwork. Okay. So let's start our class. So in the last class, we looked at the capacitance. And then we looked at how to derive the capacitance of a parallel plate capacitor, of a partially filled parallel plate capacitor. Then we also looked for the cylindrical capacitor, and for the spherical capacitor, I left it up to you guys so that you can go through this solution. Okay, and the last thing where we stopped was we were trying to develop the energy of the spherical capacitor using two methods. The first method is by directly taking the expression of the energy stored in a capacitor, which is half Q square over C. And second is from the electric field, get the energy density, and then the energy density integrated over the volume. And we saw that they are the same. I think this is where we stop. In today's class, we will spend time on looking at the Laplace and Poisson's equations. We will look at these equations, and we will do a simple derivation to get the Poisson's and the Laplace equation. And then we will see how these equations can be used to solve for potentials in a two-conductor capacitors. Remember, in our lecture 9, we said that there are two methods, right? So the first method is when you know the charge on a capacitor. From the charge, you find the potential, that is, you find the electric field, and then from the electric field, you find the potential difference, and then the capacitance. And therefore, this requires Gauss's law. Now, we are doing the second part, where the potential is known to us, and then from the potential, we determine the charge and also the capacitance. And therefore, this requires the Laplace equations. Clear? So, any questions in the last two lectures? Okay, so before going to the Laplace, let's take a poll question. Yes. So let's take a poll question. Let me stop sharing. And this is a very simple poll question. This is just a review of what we have done in the last classes. Okay, so this is for 40 seconds. It's a true or false question. Your time starts now. To find potential difference V of a two-conductor capacitor with known charge magnitude Q on each conductor, we find the electric field first, and then we find the potential difference from the electric field. True or false? 10 seconds left. 5, 1 second. Okay, so what is the answer? Yes, most of you guys got the correct answer. This we have been doing in the last class and also this class. It is true, right? Because for a two-conductor capacitor, we know the charge. And then with the charge, we found the electric field. Because finding electric field from the charge, we use the Gauss's law, or the Coulomb's law. Then once we find the electric field, then we can find the potential difference from the electric field. And that's it. So it is true. Okay, so just one more question. Time starts now. Again, it is 40 seconds. Now we have seen the capacitance. Now, how do you find the resistance of a two-conductor capacitor? It can be found once we know the capacitance and the dielectric material properties, which is separating the conductors. True or false? 15 seconds left. 10 seconds. 5. 1 second. Okay, so let's let me share the results. So how do you find the resistance of a two-conductor capacitor? We can find it from the capacitance, and once we know the dielectric material properties. Is it true or false? Yes, Mr. Abdul Majid?
It is true.
It is true, right? And most, majority of the students are correct. Why it is true? Because in the last class, I told that we are concentrating more on the capacitance because resistance you can easily get from the capacitance. And look at the time constant. RC is the time constant, which is equal to sigma over epsilon. And even you do not require to know the expression. This we just, discussed. Even if you just remember what I mentioned, that should be enough. See? So let me share it. So stop sharing the results. So if you see here, you just require to know this. RC is epsilon over sigma. So this is the material properties. So once you know the material properties and once you know the capacitance, you can easily find the resistance. And that's the reason we are not concentrating much on the resistance. Okay. So now let's go back and let's start our lecture. So Laplace and Poisson's equation. Now, what is this Laplace and Poisson's equations? So what I'm doing here, if you see, so let me just put them together probably in one page. Okay. So what we are doing here, if you see, del dot d bar is equal to rho v. So our starting point is yes, can anybody tell me?
Gaussian law.
Gauss's law. So
Gaussian's law.
starting point is Gauss's law. And this is the Gauss's law in differential form. It is in the differential form. Del dot d bar is rho v. Now, what we are doing, we are substituting d bar, which is epsilon e bar is equal to rho v, and epsilon, I'm taking it outside. So del dot e bar is equal to rho v. And this is again, as an engineers, we should understand how come you can take epsilon outside if it is in the del, if there is a del operator, it can only be possible if my epsilon is a constant. That means it is independent of the space variables. Okay, space variables, it is uniform. And this is possible just to, just for your knowledge, this is possible when we are dealing with homogeneous medium or homogeneous materials. Because in homogeneous materials, your epsilon will not change when you move inside the material, when you move in any direction, X, Y, Z direction. But you also have some types of materials which are called as inhomogeneous. And in this, your epsilon will become a function of either X or Y or Z. Okay. But this is advanced level, studies, which is not covered in our course, but just to, keep in mind. So now epsilon goes to the denominator, and now I'm using this expression. So this is the expression E is equal to minus del V, which is the relationship between electric field and the potential. Now what I'm doing, I'm putting this expression here. So del dot minus del V is equal to rho V over epsilon, or I'm taking minus outside, del dot del V is equal to rho V over epsilon. Okay, so what is this one from the identity? So del dot del V is del square V is equal to minus rho V over epsilon. And what is del square? This is called as a Laplacian. This is called as a Laplacian. For the Cartesian coordinates, this is the Laplacian. For cylindrical and spherical coordinates, it is different. And this equation is called as Poisson's equation. Got it? This is called as Poisson's equation. So again, it is being derived from the fundamental law, which is our Gauss's law. So this is called as Poisson's equation, and this is called as Laplace equation. Laplace equation is a special case. It's a special case. And what is that special case? The special case is that if I'm solving this Poisson's equation in a region where there are no charges, there is no charge density, then it becomes zero. Therefore, del square V becomes zero. And this is called as Laplace equation. Okay. So, in summary, if you see that if you want to solve the Poisson's equation in this region, which does not have any charge, then in that case, it will be del square V is equal to 0, which is the Laplace equation. But in this small region, suppose there are some charges, rho V, and you want to solve for Laplace for the Poisson's equation in this region, then you have to use the Poisson's equation, because in this region, your rho V is not 0. You have some rho V here. So then you have to go for the Poisson's equation. Now, for our course, or for this particular electromagnetic course, okay, it's an undergraduate level course. So therefore, what we do is we only try and, learn how to apply Laplace equation. Okay, so we don't go for Poisson's equation because Poisson's equations will result in a complex differential equations that we need to solve. And this is mostly for a graduate level students. So we are only looking at this. And the good thing is our capacitors satisfy this condition. Our capacitors satisfy this condition. See here. Now, if I have a parallel plate capacitor, I want to solve for Laplace equation in this region. In this region, the region which is separating the two conductors. So in this region is a dielectric region. And this dielectric region doesn't have any charges. I will, guys, this plus should not be here. It should be on the sheet. And here also it should be on the sheet. So I will try to correct it and put the revised file. So in this region you do not have. So therefore our capacitor satisfies the second condition, which is the special case, and therefore we always solve for the Laplace equation. Okay. Now, how to solve for the Laplace equation? So our first starting point is a very simple parallel plate capacitor. And how are we going to do it? Let's see. So this is my problem statement. So along y-axis, I am putting the two plates in the in the yz plane, and this is at x is equal to 0, and this plate is at x is equal to d, so that the distance between the two plates is d. Now, this plate at x is equal to 0 is placed at a potential of V1, and this plate is kept at a potential of V2. So remember, when potentials are given to you, then from the potentials, we are going to find the capacitance. So here we don't know the charge on these plates, but we only know at what potentials these plates are kept. So this is V2 and this is V1, and V2 is greater than V1. That means this is at a higher potential and this is at a lower potential. Okay. And this is the material which has a permittivity of epsilon. So now let's solve it. So first what we are going to do, we are going to first write the Laplace equation. Del squared V is equal to 0. And I'm solving the Laplace equation only in this region. So which is between 0 and d. Now, which coordinate system I have to select? Again, it's same thing. First, you need to identify the coordinate system, which would be the best that will suit your problem. So here again, it is the Cartesian coordinate system. Then you write the Laplace equation in that particular coordinate system and then solve. So here I'm writing the Laplace equation in the Cartesian coordinates, and this is equal to 0. Now, from here, what I'm doing is, if you see here, I'm saying that this and this are 0. Now, how I'm saying this and this are 0, this is from our experience and analysis. Now, if you see here, if this is kept at higher potential and if this is kept at lower potential, then how would be the electric field? We don't know the magnitude, but at least we know how the electric field looks like and what will be probably the components of the electric field, right? So from here to here, how would be the electric field? The electric field will be going away from the positive potential plate and going towards the negative potential plate. So the electric field will be in this direction as shown by the arrows. So therefore, once I know the electric field, I can identify what components it can have. So the electric field in my case, has only one component, which is the x component, right? It is only the x component. Now, with this experience, so if electric field has only the x component, then your potential V, this one, your potential V will be only a function of x. It will be only a function of x. Why? Because we know what we know, that E bar is equal to minus del V. So from here I can say, so if electric field has only x component, then my potential will also have only, it will be only a function of x. It will only be a function of x. Am I right? Did you get my point? Yes.
Yes, that's all.
To whom should I ask? Basil, tell me, did you understand this relationship, our analysis?
Yeah, somehow this is.
Somehow you understood. Okay. Because this is, see, this is very important for us. And with this, say analysis, we are making this zero. I can give you some examples if you want. I can show you some examples, but what I'm saying is correct, and I can show you those examples with our lecture, where it is in lecture 6, if I'm not mistaken. See here, this is the lecture 6. So I'm just trying to show you. See here, my potential is a function of R, right? The potential is a function of R. Now, what was the electric field which was responsible to have this potential? We used E is equal to minus del V, and we found that the electric field is 2R e power minus R square. Got it? So in this case, what I'm trying to say, that if V is a function of R, then E electric field will have only ER component, which will be a function of R, and it will be in the AR direction. So this is what we need to know. So in this example, we went from here to here. In Laplace equation, we will try to identify how the electric field will be, and from there we will know that what our potential will be a function of, for which spatial coordinates it will be a function of. Okay, so this is a good example, and if you want, there is one more example in the book where you can see. I don't remember which example is it, but I think this is taking time from us. By the way, guys, have you got the textbook?
Yes.
Yes.
Everyone. So did you get the hard copy?
Yes, yes.
Yes, doctor.
Okay, good. Where is the potential? Equation, boundary conditions. No, guys, I'm unable to locate that example. Okay. Anyways, guys, if I find it, I will let you know by email. Okay. So this is how, you know, we, based on our experience, we can eliminate
Doctor,
the V. Yeah. Yes. We can.
why did we choose the Laplacian equation for this example?
We choose the Laplacian equation for this example because that was my starting point. Because we are solving the Laplacian equation in this region. Correct? In this region. And this region is a dielectric. So it does not have any charge density. This is 0. Get my point? Because,
Yes.
because the charges are here. The charges are on the conductor. And here also it's on the conductor. But we are solving it in this region. So that's why we took Laplacian. And now, as I have explained it to you, that from our experience of how the electric field looks like and what components the electric field will have. So we have seen that the electric field will be in this direction. So my electric field will have only the AX component, and this EX, look at this, is only a function of X because it is only going in this direction. So it's only a function of X. So that's why we are saying that my potential V will also be only a function of spatial coordinate X. So therefore, this and this will become 0. And now with this, our differential equation is this one. D square V over dx square is equal to 0. Now, how do you solve this? Do the integration twice. Okay, and once you do the integration twice, you will get the constants, and then we solve for the we use the boundary conditions to solve for the constants. So if you see here, so integrating it first time, you will get dv over dx is equal to constant c1. Now integrating it this again, you will get v is equal to c1x plus c2. So my c1 and c2 are the integration constants, and this we need to find. And how we can find this? We can find this from the initial conditions or boundary conditions. What is that boundary conditions? See here. What is that boundary conditions? The boundary condition is, first, if my x is 0, if my x is 0, that is I'm here, then what should be the potential? V of x should be equal to, yes, what should be my potential here? V1. Or I would say V of 0 should be equal to V1. Then here, when at x is equal to d, my potential must be equal to this plate potential V2. Or I would say V of d is equal to V2. Got it? Yes? And also remember guys, when I'm saying here, so it is just 0 plus. It's not exactly at 0. It is 0 plus because we are in the dielectric region. So it is 0 plus, just above 0. And here also I'm referring to d minus, just before x is equal to d. So there, from the problem, we know this is kept at a potential of V2. This is kept at a potential of V1. So therefore, my V of 0 will be equal to 0 and my V of d is equal to V2. So these boundary conditions I can use to solve and get C1 and C2 values. So if you see here, now if I put x is equal to 0 here, what I will get? If I put x is equal to 0 here, V of 0 is equal to, this will cancel out and I will get only C2, right? And what is V of 0? Just now I told you V of 0 is V1. So in this case, V1 is equal to C2 and this is at x is equal to 0. Then now I'm substituting C2 in this equation. So I'm getting V is equal to C1 x plus V1. Now at x is equal to z, what will happen? This becomes V of d is equal to, this will be what? C1d plus V1. C1d plus V1. And what is this V of d? What is the potential at x is equal to d? Is nothing but my upper plate potential, which is V2. So V2 is equal to C1d plus V1, or my unknown C1 is equal to V2 minus V1 over d. And if we assume that V2 minus V1 will be what? V2 minus V1 is nothing but, yes, V2 minus V1 is nothing but the potential difference. See, this is V2, this is V1. So V2 minus V1 is our potential difference. And if I am assuming that potential difference is V0, then I will replace V2 minus V1. I will replace V2 minus V1 with V0 over d. So therefore, now your expression V is equal to, I'm substituting both in this expression. I will get it as C1 times V, sorry, not C1. V0 over d times x plus V1. And since my right hand side is a function of x, I can say that the potential as a function of x is V0 over d times x plus V1. This is the potential expression. So what does this potential expression means? That it means that if you can, so within this region, the expression of potential V of x is V2 minus V1 over d times x plus V1. So You can go anywhere in the region of your dielectric and you can find the potential. So for example, what is the potential at this point? What is the potential at this point? What is the potential at this point? So if to find the potential at this point, we should only know this. What is this? Is the x value. So if this point is like A, so it is at a distance A, then the potential will be V2 minus V1 over D times A plus V1. So this expression will allow you to find the potential anywhere inside the plane. And this is the advantage of Laplace equation, or finding the capacitance with the second method. With this, the extra byproduct is that you can get the potential expression that you can use to find the potential inside this region. And our first method doesn't give that. And you can also cross-check whether this equation is correct or wrong. How do you cross-check this equation? Can anybody tell me? Yes? Thabit, can you tell me? How can you cross-check this equation?
Again, doctor?
How, my question is, once we get our potential equation, is there a way to cross-check and assure that this is correct? Once you get the expression, is there a way to cross-check to assure that whatever you have got is correct or wrong?
I'm not sure.
No, Thabit, this doesn't require any knowledge of electromagnetics. This is just from the mathematics. You have some boundary conditions and you have an equation which satisfies that boundary condition. Okay, Abdul Malik, you raised your hand.
Yes, doctor, we can substitute x with 0 and x with d.
Exactly. Because see, Thabit, we got this expression of V of x by using this boundary conditions. These two boundary conditions. So therefore, once we get this answer, to cross-check, you can put this boundary conditions back into your answers and cross-check whether it is right or wrong. So if I put x is equal to 0 here, this term will be gone. And my potential is becoming V1. Is it correct? Yes. At x is equal to 0, the potential must be equal to V1. Correct. Now at x is equal to d, if I put d here, then d and d cancels, and V1 and minus V1 cancels, and I will get V2. So therefore, at x is equal to d, my potential is V2, which is correct. So this is how you can cross-check and make sure that the expression you got is the correct expression. Okay? And by the way, you have used this in your experiment number 1 of capacitors. Now we are deriving it, but you have used this one. Okay. Now, once the potential is known to you, then you can find the electric field, which is E bar is minus del V, which is equal to minus dou rho V minus dou V over dou X times AX. Now, if you find the partial derivative of this with respect to X, okay, so we are not using V2 minus V1, we are using V naught of D, we are using this one. So if I partially, find the derivative of this with respect to X, I will only get V0 over D. So it is V0 over D times AX. And why it is minus, this is coming from the expression. And if you see, this is consistent because our electric field is in this direction. So it should be negative because AX is negative. So E is equal to minus V naught over D times AX. This is our electric field. Now, what we are saying that once I get the electric field, then how can you find the capacitance? Now, this is becoming straightforward. Once you know the electric field, you know V. Once you know V, you can find find the charge if you want. You can find anything. So this is an example where, because we did not know what was the charge on the plate, right? We did not know what was the charge on the plate. We only knew the potential. Now, can you find the charge on the plate? So this is the next example. It is saying that if this is my electric field of my capacitor, can I find the charge on the lower plate of the parallel plate capacitor? Can I find the charge? Now, think about it. How can you find the charge? Because we know that to find the charge is integral rho s ds. See, it is integral rho s ds. But first, we need to find rho s. How can you find rho s? How can you find rho s? How can you find the surface charge? Now, this you can find it by, okay, let me draw it here. This you can find it by applying the boundary condition at the conductor. This is the conductor and this is the dielectric. So apply the boundary condition here. So at this x is equal to 0. So this is the boundary. So what does the boundary condition says for if you have dielectric and a conductor? It says that D1, yes. Yes, what does it says? Does anybody remember for the conductor dielectric boundary? Yes. It says that, what does it says? It's C.
D1x equals rho s.
Yeah, it is written here, but you should understand how I'm getting here. Because there is no electric field here, right? We know that D1n minus D2n should be equal to rho s, right? So here there is no D2n because in the conductor there is no electric field, so it is 0. And that's why D1n should be equal to rho s, or E1n should be equal to rho s over epsilon. And what is E1n? E1n is the normal component of the electric field in the dielectric. And in our parallel plate capacitor, we only have this component. So we only have this component, right? And this component is our minus V0 over D times AX, which is already our normal component. So therefore, the normal component magnitude, the normal component, yeah, you can say the normal component, this EX value must be equal to the rho s over epsilon, because this is our E1x, which is equal to minus V0 over D, and this is rho s over epsilon. That's why I'm getting this one. And from here, I can find rho s. So my rho s is epsilon V0 over D. If you want to keep minus, you can keep minus because this is at the lower plate. So therefore, your charge will be negative, and that's why you're getting this minus. And if you integrate over the surface, what will be the surface? That is the surface of your sheet, this one. And if the surface area is S, then it will be minus epsilon naught S V0 over T. And this is what we have seen in our previous example, that the charge Q is minus epsilon S V0 over T. So this is my charge Q. Now you can find the capacitance in whatever way you like. We know, you know, C is equal to Q over V, right? C is equal to Q over V. But in this case, it is V0 because it's the potential difference. Now you can put your Q value. See, you can put your Q value, which is epsilon S0 V0 over D over V0. And this will become epsilon S0. Sorry, there is no S0. So which is epsilon S over D. This is your capacitance, which we got it from the second method, Okay. So summary. Summary is what? The summary is we found V using Laplace equation. Then we found the electric field from the potential, and then we found the charge from the electric field by applying boundary conditions. And then from this, we can find C. So in a short form, we first found V. From V, we found electric field. And from electric field, we found the charge Q and then the capacitance C. This is my method 2. In method 1, Q was given to us. So from Q, we found E. And from E, we found V. And from V, we found C. And remember, here V is referring to potential difference. And here, this V is referring to only potential. So these are the two methods. Now the advantage of method 2, as I have told, the byproduct is you get a general expression of potential inside your dielectric material, and you can find potential anywhere inside your dielectric material. This method will not give you. Clear? So these are the two methods. So now what we are going to do is, for other examples, we are not going to go and find the Q. We are not going to go and find Q by using boundary conditions and from Q to find the capacitance. So these steps, I'm leaving it to you. So we will just stop here. Here, we will stop. Okay, so from here, or we can find here and stop here. But this, once you get the electric field, apply the boundary condition at the conductor dielectric interface to find the charge Q on the plates or on the conductor, and then from there finding the capacitance. We have did it for this example of a parallel plate capacitor, but for others, you can do it at home. Okay, so now we have one more example. So if you see here, this is a spherical capacitor. It's a spherical capacitor. Now, if you see in the spherical capacitor, you have an inner conductor, which is kept at a potential of VA. Outer conductor is kept at a potential of VB. And the potential difference between these two is V0. That means V0 is VA minus VB. That means VA is positively charged and VB is negatively charged. And we need to find the potential expression anywhere in this dielectric region whose permittivity is epsilon, and also the electric field. Okay, what is the electric field? Okay, so just give me a minute. So how can you do this? How can you do this? Again, because it's a spherical capacitor, then which coordinate system would be the best?
Spherical coordinates.
Spherical coordinate system will be the best. So therefore, my Laplace equation will be solved in this region, which is between A and B, because this is B radius, this is A radius. So it will be solved between A and B. This is the Laplacian, and the Laplacian will be in the spherical coordinates. But the good thing is, let's go and just look at our knowledge and our experience. So what does our experience says? How would be the electric field in our experience, from our experience? The electric field will be radial. It will be going away from the inner conductor and towards the outer conductor. It is going like this. Like this. So it will be radial. That means it has only R term. So your electric field has only R term. Oh, sorry. It has only R term. So it is ER, AR. And not only that, since it is moving in the R direction, it's a function of only R. So therefore, your potential, which is, yes, Zuhair.
Doctor, can I get out of the class because it's time due and I have something to do?
Yeah. It's okay. Okay, guys, let's do the following. I think we would not be able to finish now. Maybe I will just quickly talk about it in the next class and then we will continue. Okay? We will continue in the next class.